Hey everyone, we're about to take a deep dive into something you use every single second, but probably don't think about much, your auditory system. I mean, this is one of the most mind-blowing pieces of biological engineering out there. It's so good, so sophisticated, that it's literally the blueprint for almost all of our modern audio tech.
So, have you ever really stopped to think about it? How does this fleshy thing on the side of your head take nothing more than vibrations in the air and turn them into the powerful emotion you feel from music or the complex understanding of a conversation? It's kind of magic when you think about it.
Well, here's the thing. What you've got attached to your head is, and I'm not exaggerating, the most advanced audio processor ever built. Seriously, it's so much more than a simple microphone. So, let's follow a single sound wave on its incredible journey and see just how it all works.
Okay, so our journey starts right at the beginning, the exact moment a sound wave actually reaches you. Now, the first job your ear has isn't just to hear the sound. Nope, it's to figure out exactly where that sound is coming from in 3D space.
And that's the job of your outer ear. You know, the part you can actually see, the pinna. It's not just there to hold up your sunglasses, Its weird, complex shape is actually a super sophisticated biological antenna. It catches sound waves and funnels them right into your ear canal. But honestly, that's not even its coolest trick.
See, your brain creates this amazing 3D sound map of the world around you using three main clues. First, there's timing. If a sound is on your right, it's going to hit your right ear just a tiny fraction of a second before it hits your left. That's the interaural time difference. Second, there's volume. Your own head actually creates a sound shadow, so that same sound will be just a little bit quieter in your left ear. They call that the interaural intensity difference. And third, and this is super clever, those unique folds in your ear subtly color the sound, changing the frequencies just enough for your brain to tell if it's coming from above you, below you, or even behind you.
And here's where it all connects to the tech you use every day. This amazing biological system is exactly what we've learned to hack. Think about virtual surround sound, or spatial audio in your headphones, or those incredibly immersive video games. They all work by digitally recreating these exact same tiny differences in timing, volume, and frequency to trick your brain into thinking sound is coming from all around you. It's pretty wild.
All right, so the sound has been located. It's traveling down the ear canal, and then, bam, it hits a major roadblock. At this point, the auditory system has to solve a really tough physics problem. How do you get energy to move efficiently from a thin medium, like air, into a really dense one, like liquid?
Just think about trying to shout at a friend who's underwater. From above the surface, most of that sound just bounces right off, right? Well, that's the exact problem here, because your inner ear is filled with fluid. Without some kind of power boost, almost all the sound energy would just be lost at the barrier. We'd basically be hearing the world as if we were underwater all the time.
But of course, nature has an incredibly elegant solution, the metal ear. It's basically a brilliant little mechanical amplifier. The sound wave hits the eardrum and makes it vibrate. That vibration then gets passed along to three of the tiniest bones in your entire body, the malleus, incus, and stapes. You might know them as the hammer, anvil, and stirrup, the ossicles.
So, just how powerful is this tiny little lever system made of bone? Get this, it takes the large but very weak vibrations from the eardrum and focuses them down into small, really powerful vibrations. This gives the sound an incredible boost, an amplification of about 28 decibels, and that is more than enough power to ram that sound wave right into the fluid of the inner ear. Problem solved.
Okay, so with that 28 decibel kick, the vibration finally makes it into the inner ear, and it arrives at the most complex, the most intricate part of the entire system, this amazing spiral-shaped thing called the cochlea. This, my friends, is where simple vibration gets turned into the rich world of sound that we perceive. So, here's what goes down inside the cochlea. The vibrations make a wave in the fluid. This wave travels along a thin strip of tissue called the basilar membrane, making it vibrate too. Now, this membrane is amazing. It's tuned kind of like piano strings. Different spots along it resonate with different frequencies. High notes vibrate one end, low notes vibrate the other. And as this membrane is wiggling, it bends thousands and thousands of microscopic hair cells. That bending, that is the magic moment. It's the point where mechanical motion finally gets converted into an electrical signal that the brain can actually understand.
You know, the best analogy I've ever heard for this is a prism. Think about how a glass prism takes a single beam of white light and unrolls it into a beautiful rainbow of individual colors, right? Well, the basilar membrane does the exact same thing, but for sound. It takes a complex sound, like a full chord played on a guitar, and it unrolls it into all its individual frequencies, all laid out in order from high to low. It's a biological, mechanical spectrum analyzer. It's incredible.
And this shows you a really fundamental difference between how our bodies work and how our technology works. A man-made system, like a microphone and a computer, it captures sound, turns it all into a single electrical signal, and then a processor has to work really hard to analyze that signal for frequencies. The human ear, it's way more elegant. It does the frequency analysis first, mechanically, with the basilar membrane, and only then does it convert that already sorted spectrum of vibrations into electrical signals. It's just a totally different and, you could argue, a much more efficient approach. So now, the cochlea is sending this absolute fire hose of frequency data up to the brain. But here's the twist. The brain doesn't actually process every single bit of that information. Not even close. Instead, it's learned to take some really clever shortcuts. And this brings us to the super cool field of psychoacoustics.
Psychoacoustics is basically the study of the gap between what sound physically enters your ear and what your brain tells you you're hearing. See, your hearing isn't some perfect high-fidelity recorder. It's an amazingly efficient filter. Evolution has designed it to zero in on what's important, like speech or a predator, and just kind of ignore the rest.
Okay, one of the biggest shortcuts your brain uses is something called spectral masking. Here's the deal. When a really loud sound hits that basilar membrane, it doesn't just vibrate one tiny spot. It excites a whole neighborhood of hair cells. Now, if another, much quieter sound tries to sneak in within that same vibrating region, it gets completely drowned out. The loud sound just overwhelms the system, and your brain never even gets the message that the quiet sound was there. It's like it was invisible.
And get ready for this, because this is the billion-dollar idea. This biological flaw, this masking effect, is the entire secret behind MP3s and all modern audio compression. Seriously. Codecs like MP3 and AAC use these psychoacoustic models to analyze a song, figure out which sounds are going to be masked by louder sounds, and then they just delete them. They throw that data away. The logic is simple. If your brain was never going to hear it anyway, why waste the digital space?
There's another cool trick called temporal masking. It's all about timing. Your brain is hypersensitive to the very start of a sound. But right after a loud sound stops, there's this tiny little window of time where your hearing is less sensitive, almost like your ears are resetting. And yep, you guessed it, audio codecs exploit this too. They can hide little bits of digital noise or other imperfections in those moments, knowing you'll never notice.
So let's just take a step back and look at the whole picture. We've followed this absolutely incredible journey, all the way from a simple wave rippling through the air to a complex signal firing in the brain. I mean, think about it. A simple wave in the air gets caught and pinpointed in 3D space. Then it's mechanically amplified to punch through a fluid barrier. Then it's unrolled into a full frequency spectrum like a rainbow. And finally, it's converted to electricity and filtered using the brain's own built-in compression software. It's just this beautiful cascade of physics, engineering, and neuroscience all happening at once. And all of this just leaves us with one final, really exciting question. For years, we've been hacking our own hearing to create things like MP3s and VR audio. We've been reverse engineering our own biology. So as our understanding gets even deeper, what's next? What is the next generation of audio going to be like when it's built on an even better understanding of this incredible blueprint inside our own heads? What will it sound like? And what will it even feel like?